Here are some useful sums. The sum of 1s when k runs from 1 to n is just 1 plus 1 plus 1 n times, and we get n. The sum of k when k runs from 1 to n, which is also 1 plus 2 plus 3 plus 4 plus n, equals to n times n plus 1 over 2. Example. We already expressed this summation as 5 times sum of k when k runs from 1 to n plus 7 times the sum of 1 when k runs from 1 to n. But now I know that the sum of the k's when k runs from 1 to n is n times n plus 1 to the power of 2. According to that, and I also know that sum of 1 when k runs from 1 to n, using this, is n. As you can see, on the left side you have a sum, and on the right side you have expression of n. But pay attention, you will get expression of n only if, as you can see, the upper index on the sigma is n. Let's try to find the value of this summation. You can see that this is exactly the same as the one that it's written on the right here with n equals 6. So we plug 6 for n and we get 21. Here is the picture for that. As you can see, the number of yellow squares, which is also the number of the blue squares, is 1 plus 2 plus 3 plus 4 plus 5 plus 6. How many squares do we have here? The total number of squares here is the following. Here we have 7 and here we have 6. So the total number of squares here is 6 times 7. But the summation is only the number of the yellow squares or the number of the blue squares. But this is exactly half of 6 times 7, which is 21. Another way to view that is doing the following. Here is the summation. Now we are going to write the summation in the reverse order. Now we're going to add that. When we add it up, we get that the sum of each pair here is 7. But how many of those do we have? We have 7 plus 7 plus 7 6 times. It means that here we have 7 times 6. But our sum is exactly half of that, and we get again 6 times 7 over 2. If instead of 6 we will take n, we actually get the easy proof of why the summation of k when k runs from 1 to n, which is also 1 plus 2 plus n, equals n times n plus 1 over 2. In this case, we know that the summation of k runs from 1 to n of 1 is just n. And we get here c times n. This also shows me that if c is a constant, then the sum of c when k runs from 1 to n is just c times n. It is another summation that appears really very often, so it's just better to know that the sum of a constant when k runs from 1 to n is just n times the constant. Here are more useful sums. The sum of k to the power of 2 when k runs from 1 to n, which is also 1 to the power of 2 plus 2 to the power of 2 plus n to the power of 2, can be written as an expression of n. And this expression is n times n plus 1 times 2n plus 1, all that over 6. And then we also have an expression for this, for the summation of k cubed when k runs from 1 to n. And this one is n times n plus 1 over 2, all of that to the power of 2. Example, let's write as a function of n the following sum. The sum of k to the power of 2 plus 2k plus 3 when k runs from 1 to n. First we will use the linearity to write it like this, and again we are going to take out the constants from the summation. Now we are going to use what is written up. This summation is this one. This one is this one. And we know that the last one is just the sum of 1, which is n. And we get that. Again, as you can see, we started with a summation that has upper limit of n, and we can express that as an expression, or a function if you want, of n. Example, let's now evaluate the limit of 1 over n cubed times the sigma of k runs from 1 to n of k to the power of 2 plus 5 when n approaches infinity. First we have to work out the summation. We have to split it again to two sums. The sum of k to the power of 2 plus 5 is the sum of k to the power of 2 plus the sum of the 5. Now I'm going to use this for the first sum, and I know that the sum of 5 when k runs from 1 to n is just 5 times n. And I get that. First of all, as you can see, I want to get rid of this 1 over 6, and then I'm going to divide everything by n cubed. So I have to divide the first term by n cubed, and then the second one by n cubed. Now I want to show you a trick that will be very useful later in calculus. There is no need to multiply out everything. And here's what I'm going to do. I'm going to write n cubed as n times n times n. One n I kind of lying down under the n, another one under n plus 1, and another one under 2n plus 1. In the last term, I'm just cancelling out the n, so 5n over n cubed is 5 over n to the power of 2. Now I'm going to use property that we know from limits. Limits of a product is the product of the limits. So I can actually take the limit of the first one, n over n, and I will get 1 when n approaches infinity. Then I will take the limit of the second one, which is n plus 1 over n, and I will get that the limit is 1 when n approaches infinity. And then I will take the limit of 2n plus 1 over n. When n approaches infinity, I will get 2. So here's the total. There's 1 over 6, which is just a constant, times the first limit, which is 1, the second limit, which is 1, the third limit, which is 2, and we know that 5 over n to the power of 2 when n approaches infinity is 0. When we add everything up, we get 2 over 6, which is 1 over 3.